Layer 2 data centers forward frames to connected hosts based on the destination MAC address of a network frame. When a host in a Layer 2 data center is required to communicate with another host within the data center and within the same Layer 2 broadcast domain, the source host sends a data frame to the MAC address associated with the destination host. If the MAC address of the destination host is unknown, the source host uses an Address Resolution Protocol, or ARP, request to query the remote MAC address associated with the destination host's IP address. The response to the ARP is stored in the source host's ARP table, where it can be used for future transmissions. Switches that relay the frames between hosts populate a MAC address table, or switching table based on the MAC addresses on frames that enter switch ports. In this manner, a switch can assign an outbound port to each MAC address in the Layer 2 domain and can avoid broadcasting Layer 2 frames on ports that do not connect to the destination hosts. Because of the redundant links present in a switching domain fabric, the potential for broadcast loops requires the implementation of loop prevention protocols. One of the most common loop prevention protocols in a switching domain is Spanning Tree Protocol, or STP, which manages the forwarding state of Layer 2 ports within the network and blocks forwarding on ports that could potentially create a forwarding loop. In the event of an active forwarding link failure, blocked ports can be enabled to pass traffic. Because of this blocking nature of STP, the implementation of STP within a switching domain has the potential to greatly reduce the forwarding capabilities of a fabric by blocking ports. When traffic is required to transit between Layer 3 domains and a Layer 2 fabric, a default gateway is often used as the next hop to which hosts forward traffic. The default gateway acts as a gateway between different Layer 2 domains and functions as a Layer 3 router.
The concept of routing in a data center is based on implementing a Layer 3 fabric in place of a Layer 2 fabric. In a Layer 3 fabric, packets are forwarded according to IP next hops within the routing or switching devices. A node in the fabric forwards traffic toward the destination host based on routing table entries, which are usually learned through a dynamic routing protocol. With a Layer 3 fabric, the MAC address of the transit frame changes at each physical hop. Ideally, leaf nodes in a Layer 3 fabric should have multiple forwarding paths to remote destinations. Loop prevention in a Layer 3 fabric is provided by dynamic routing protocols such as OSPF, IS, and BGP. The Juniper Apstra software uses external BGP or eBGP. Many vendors implement routing solutions that enable equal cost multipath or ECMP load sharing. The proper configuration of ECMP within the Layer 3 fabric supports the use of all links for forwarding, which provides a substantial advantage over STP loop prevention in a Layer 2 fabric. Because the Layer 3 fabric is a routed domain, the broadcast domains are limited in scope to each individual link. With a Layer 3 fabric, hosts attached to the edge or leaf nodes do not have direct Layer 2 connectivity, but instead communicate through Layer 3. The example shows the desired routing behavior of a leaf node. Ideally, each leaf node should have multiple next hops to use to load share traffic over the IP fabric. Note that router C can use two different paths to forward traffic to any remote destination. Within an IP fabric design, each spine node should have a connection to each leaf node. In the event of a spine node link or node failure, leaf-to-leaf connectivity is maintained. In the case of multi-homed sites, each spine node should have multiple paths to the remote site and should load balance traffic to the remote host across all leaf nodes that connect to the remote site. Your IP fabric forwards IP data only. Each node is basically an IP router. To forward IP packets between routers, they need to exchange IP routes, and therefore you have to make a choice between routing protocols. You want to ensure that your choice of routing protocol is scalable and future-proof. From the table displayed, you can find that eBGP is the natural choice for a routing protocol and is implemented when using Juniper Apstra software. The capabilities of OSPF and ISIS may be sufficient for many environments and deployment types, depending on the end role of the IP fabric. For example, an IP fabric that connects directly to all host devices and maintains routing information to those hosts would benefit from the scale capabilities of eBGP. An IP fabric that is deployed as an underlay technology for an underlay overlay deployment is required to maintain routing information related to the local links and loopback addresses of the fabric. It does not maintain routing information pertaining to end hosts or tenants. In the latter scenario, an interior gateway protocol, or IGP, may be sufficient to maintain the necessary routing information.